So what are these examples? I'll cover 3 examples to illustrate how do we set a distance relay. You know, as you remember, distance relay has assist. At least you need to have 2 zones to protect a line, and the third zone is normally is taken as a backup for the adjacent line, longest adjacent line. And the zones here, like zone 1 normally covered up to 30% of. So what I want to, I have a system here, a line, transmission line. At the end of this transmission line, I have another transmission line and another with the transformer, then another transmission lines here. Okay, so it could be continued probably here. Okay, and I want to find the settings for relay RAB. So I want to find distance relay settings for this relay. And these relays, normally for each line, I have a distance relay looking in this direction. I have another distance relay looking at this direction. Similarly, I have distance relay looking at this direction, another at this direction. Okay. So these are the distance relay for each line. For this relay, it has to have a zone 1. So zone 1 covers up to 80% of the line. So this is zone 1, 80% of the line covered by zone 1 for relay. And this zone, which covered 80%, for any fault within this 80% of the line, from A up to 80% of line this, it will act instantaneously. And that's zone 1. For zone 2, would cover the remaining 20%, which is not covered by zone 1. And so how do we add line 1 plus 20% extra? So it would cover up to, okay, that sits as zone 2, 120% of the line impedance that you are protecting. But in such a way, it shouldn't go beyond 50% of the next adjacent line. So this has not to be more than this, or 50% of this. And the third, so this 20% assures that any fault within this line, protected line, will be detected. The third zone is as a backup. So the backup zone 3 covers whole line, this line, plus the 100% of the second line, longest line. So if you compare this 90 and this 50, the J90 here becomes larger. If you take the impedance of the two, the J90 becomes, let me check the adjacent lines. I think it's not 90, I think this is J9. Okay, this is J9. Okay, so this section becomes bigger in impedance as compared to this, and as a result, this becomes the longest line. So if you protect the longest line, adjacent line, this automatically covers the shortest line. So that will cover up to AB. Zone 3 will cover AB. It's 100% of AB. It will take sometimes addition of the two, 100% of AB plus 120% of PC. This is one way. A second way is 100% ZAB will take ZAB plus ZBC plus we want to add more 20% of this, so sometimes we multiply this by 110% or 120% of the sum. So take 10% of this, 10%, so that's also 20% of the remaining. And this is zone 3. So zone 3 has a backup, but zone 1 and zone 2 as a primary to protect this line, protected line. So 120% of course of ZAB impedance. And this is also ZAB. So these are the settings that I want to calculate. But these impedances has to be referred to the secondary side and of the CT and VT of the distance relay. So we multiply them by TR factor, the transformation factors. So what I am given here, I'm giving the voltage at this line, which is 138 kV, okay, at this bus, line to line. Positive sequence impedances are shown. This is our positive sequence impedance. And you know, the distance relay measures the positive sequence impedance from the relocation to the fault point. So I have in settings, we have to use the positive sequence impedance of the lines or components. Transform impedance is given in ohms as viewed from 138. This impedance of this is referred to the 138 kV side. Okay. Assume that the maximum load at the relay side, so the maximum load here, so load here is 120 MVA. So this is my load, maximum power flow in the line, and the CT ratio, assume the maximum load at the relay site is 120 and select the CT ratio accordingly. Okay, based on this, I would select the CT ratio. Available distance relay has a zone 1 and zone 2 settings from 0.2 to 10 ohm. These are the range of zone setting I can select from 0.2 to 10 ohm, and zone 3 from 0.5 to 40 ohm, and steps of 0.1 ohm. So these are the range of available settings for zone 2, 1, and zone 1 and zone 3. The maximum torque angle can be adjusted to 975 or 80. So I have only 2 settings, but in real relays you will have more angle settings to choose from. I'll show inshallah at the end of this lecture the one numerical relay from the GE company. Remember that zone 3 of the relay must back up the line BC as well as the transformer. So if I choose the setting to cover this, it automatically covers the smallest impedance components. So I'll start now choosing the CT and VT ratios. And because the system is 138 kV, okay, so the VT will be 138 kV to 120 volt. Okay, that's the standard output of a VT. And the load is given to us 120 MVA. Okay, I can now find the current, rated current. I got it 502, so it's almost 500. So I'm choosing either 600 to 5 or even 500 to ampere with respect to 500 is negligible. Okay, so it's even 500 to 5 is reasonable, or I can go to 600 to 5 if you want. For the voltage CT, for the CT, 138 kV as a primary rated voltage to a secondary fixed 120 volt according to American standard. So I got now the CT ratio and VT ratio. Now I can find the transformation ratio, the CT ratio over VT ratio. I got this is the transformation ratio, and then I can start finding the zone. Zone 1 is set to 80% of line AB, and so it means it has a reach of, it reach up to 80% of the line. We call sometimes reach as the zone coverage. Okay. So zone 1 is 80% of ZAB, of the line, protected line impedance, which is 3 plus J4. Okay, and multiplied by the transformation ratio in order to to see how the relay sees the measured impedance of the line. Okay, it will see this 80% of this as 2.79 and angle is 85. So the settings, because available in steps of 0.1, so the settings is 2.8 and angle is 80. Because we have 75 and 80, I'll choose the closest one. In this case, 80 degrees is the closest to this. We call this sometimes also the characteristic angle, okay, instead of just an angle. So I got the zone 1 setting, zone 2 setting in the same way. It will be 120% of ZAB and 120%, which is 1.2 times ZAB times transformation ratio. I got this one. So from this 4.2 as my setting for zone 2 reach setting, and angle settings is also 80 degrees. Zone 3, I'll take it. It acts as a backup to protect the longest adjacent line, which is line BC in this case, and so I have taken 110% of the sum of these two impedances. Sometimes can take ZAB plus 120% of this, as I will show you inshallah in the next slides in another examples. So if you substitute here, I'll get, you added these two impedances times 1.1 times the ratio, I got this. So the settings will be 8.7. Okay. This is an alternative way. Say we can set also ZAB plus 120% of ZBC all times transformation ratio. If you do this, I'll get almost same. Okay. So either you take this approach or this approach, it will lead closer to each other. So in this setting, I'll choose based on this. No. Okay. I'll choose 8.6 ohm. So why it's not 8.7? It's fine because always we have a 10% already or 20% roughly. Okay. So you can choose also 8.7. So the angle setting will be 80 degree, and the distance relay settings. Now in summary, this is zone 1 setting, zone 2 settings, zone 3 settings, all forward looking. So all are looking in the forward direction, because in our relays we can also set them to look backward. Okay. So this is the finish from settings. As you can see, it's straightforward, easy to do. Okay. And the characteristic angle or relay angle is 80 degrees for all the zones. Example 2, the same example, but I want to see how the load, I want to draw these zones, okay? And I want to see how the load impedance location with respect to these three zones, okay? So in this figure, using the relay settings determined earlier, plot the three zone settings, okay, on Rx diagram. Also show the 120 MVA load. In the Rx diagram, you may assume a load power factor 0.8 lagging. Okay, plot the load impedance when the load is flowing into the line. So when the load into the line means this power flow here. This is the line, protect line into the line, which is in this direction. This is S load. Or when it is flowing into the line and when it is flowing into the bus in this direction means this flowing into the bus. Okay, this is S load for the second case. I want to see, draw the when the power flow in this direction or when power flow in this direction, how the load impedance is located within the Rx plane. Okay. Is there any problem in setting a directional impedance relay with this load? So I want to use a directional impedance characteristics. Okay. If perceive a problem, what solution you might suggest? We will see if we have a problem of load encroachment or not. Now we'll do the same thing. Okay, we need to find the load impedance, how the load impedance in ohm and Z. So load impedance, V line, 2 lines, voltage square over S, okay, S of the load. So give me the impedance. This is the magnitude and the angle of this impedance from the power factor, right? Power factor 0.8 lagging, so I can find also the angle of this will be 36.87. This is the angle of the load. So this impedance referred to the primary side, okay, and the primary side. So I have to refer it to the secondary side of the CTVT to see how the relay sees this load impedance. So I will multiply it by the transformation ratio, TR. And that gives me the relay sees this impedance 158 as 13.8. This is as measured or seen by the relay. Now the impedance, the C relay is 13.81, angle is 36.8. So when I draw this impedance, this is X plane axis and this is the R axis. And when I draw these impedances of the directional impedance relay, so zone 1 covers up to, from this example, is 2.8 ohm. So I'll draw a circle of radius 2.4 ohm. Okay, so this point radius here, that's 2.4 ohm. And I'll draw a circle. And so then I'll draw a circle of 4.2 ohm. This is now the point 4.2 ohm from the 0 to here, 4.2 ohm, and the last one is the zone 3, which is at 8.6 ohm. So 8.6 is this point. Radius here is 8.6 ohm. And the angle here is 80 degrees. The angle from here to the angle characteristic, this is 80 degree. Okay, of this line. And this is the characteristic angle. Okay. Now, where we, because it's directional, the characteristic angle represent the direction, the maximum torque line. Okay, which is this line now. And so this is the 80 degree. And so the 0 torque line is 90 degree with respect to this. So I'll draw this 90 degree with respect to this line. And that's the direction characteristics. So really we'll see only forward looking impedances. So any impedances here, it will not be seen by the distance relay. Okay, and the load, if I want to draw the load, load is impedance 13.8. 13.8, as you can see, is higher than zone 3. This zone 3 is already 8.6. While this is 13 ohm. 13 is, so it's beyond the zone 3 reach, so it is somewhere here, and the angle of this is 36.87. So this is the load location impedance when the power flow from the bus to the line, when the power flow here in this direction. It is in the same as direction as the sitting direction, which is in this direction. So the trip direction in this direction, and the power flow is in the same direction. So on the impedance looking in the first quadrant of the XR axis. Now, when the power flow reverse means, what does the power flow reverse means? Current has reversed. When a current has reversed with respect to a voltage, the impedance also will be seen as 180 degree with respect to this, because at the end, impedance is voltage over current. The current is 180 degree reverse, so this also will change by 180 degree. So if you subtract 180 degree from this, so or add 180 degree, I get this direction. So this is the impedance, which is also 13.8 length, also 13.8, but at angle of 36.8 minus 180. Okay, this angle. So the angle here from 0 axis to that is 138, 180, 138 or 36.87 minus 180. And that's it. So from this characteristic, it looks like the relay will not, because the load impedance will not fall inside the zones, any of the zones, the 3 zones. So the relay, we will not have any problem of load encroachments. So there is no load encroachment problem, and hence the settings that we have taken. So the directional characteristic can be used in this case. Now, in this example, I have, let's say, in feed for a bus A, and then I have a line, okay, and I want to, this is the end of the line, I want its positive impedance of this line is 4 plus J40 is 0 sequence impedance is this, Normal transmission line positive and negative impedance is same, so this is also same as negative. The generator side is positive sequence reactance is given, or impedance, and they also the zero sequence impedance given. So now we want to find zone 1 and zone 2 of this of the relay at bus 2. So I want to find this zones 1 and zone 2. If the maximum load in this is 10 MVA, so the load here is load maximum, okay, equal to 10 megawatt. What are the settings zone 1, zone 2? For this line, you may assume that the available distance relay is the same as the previous problem. No, what I did, I just assume a relay setting from 0 to 50 ohm in steps of 0.1, and the available angle setting or the is 70, 80, 85. Assume that the generator voltage is 113.8, so this is a 13.8 kV output here. And the CT ratio is given, and the VT ratio is 13.8 to 120. And we can check also whether this is suitable or not. So the full load current is 100 and should be 10 instead of 120. This is wrong. It should be 10. Because the maximum power, the maximum load is 10 MVA. Okay, so this has to be 10 times 10 to the power 6, because 10 megawatt over √3 line-to-line voltage 13.8 kV. I got this, so a CT ratio 500 to 5 is suitable. And the impedance transformation, CT ratio over VT ratio, I got this. Now zone 1 settings, 80% of the protected line positive sequence impedance, which is this 4 plus J40, okay, times the transformation ratio, I got it here. And so settings will be 28 angle closest to 84, in this case is 85 setting. And zone 2 is 120% of the protected line impedance, and I got this one, so the setting is 42 and the angle setting is same. For now, because there's only, I cannot set zone 2 because I don't know zone 3, because I have to know the longest adjacent line, which is not available in this problem. If I want to set as a backup for the next line, I want to see now the load impedance, because at the end I would like to see if it falls inside the trip characteristic or not. So the load impedance, which is line-to-line voltage square over 10 MVA times the transformation ratio, this is the impedance as seen by the relay, okay, and the power factor it's 0.8 lagging, so that's the angle of the load. And now we'd like to check the 3 characteristics. I will check if we use a directional impedance characteristic, would that be suitable or not? Okay, so when zone 2 setting, which is the biggest zone now in our case, is 42 ohm reach, but the load is 16. So load is inside, load impedance is smaller than the zone 2 or even zone 1. So load becomes inside zone 1, so it will trip instantaneously in this case. So this directional relay is not suitable in this case. It's not suitable because the load impedance will fall inside zone 1 and zone 2 characteristics. Okay. Now if we use more characteristic, which is a circle that passes through 0, and we choose now zone 1 and zone 2. So zone 1 something like, if I would like also to draw zone 1 is something like this is zone 1. But zone 1, okay, normally we can check zone 1 and zone 2, and this is zone 2. But zone 2 has more coverage, so the probability of a load falling into zone 2 is more. So I will check just with the longest reach. So if I have zone 3, I will check if the load falls inside zone 3 or not. Because for zone we have a problem with load encroachment, we have to find a solution, or this will not be suitable. So I tell you, I'll draw the line characteristics, the load characteristics. The load impedance falls on a line that makes an angle 36.87 with respect to reference. So this is the load line, so it's load somewhere here, but I don't know if it's inside or outside. So with this, I'll see the line of the load. When does it cross? At where does it cross the directional mode characteristic? So let's say at the point ZB. So I want to see the impedance from here to here. Okay, if this impedance smaller than this, so means this Z load greater than that, means there is no problems here. But if Z load becomes smaller than ZB, means Z load is somewhere here, so we have problem. So how do you find this ZB? We know this is now our setting, which represents the diagonal, the diameter of the circle. So we know this from the settings, zone 2 setting. So zone 2 setting was 42. So we know this is a 42. The length of this red line is 42 ohm. And if you link a line between any 2 points in a circle that pass to the diameter, so this is diameter points, and if you draw any line, if you link these two, it makes 90 degrees. Okay, and as a result, I know this angle, which is 85, is our settings. Okay, angle of the settings. And we know this angle, so the angle difference is also known, this angle, the difference between this. So what is this value? Okay, I know this, I know the angle. So it's like a triangle. I need one so this angle is, so this value from here to here is Z, which is this, okay, times cosine angle phi minus theta, which is cosine the differences. And I want to find, this is zone 2 in this case, impedance. And I know this angle, I can find ZB. So substituting zone 2, impedance cosine 85 minus 36, I get 26. So this point is 26, but this point is 13, 16.57. This is 16.57. And now this becomes 26. So what does 16 smaller than 26? So means this will be inside the trip characteristic of distance relay. As a result, this is also more is not suitable also. You will have load encroachments. So if we use this, we can solve this problem using quadrilateral characteristics and or polygon type. So in this case, if I use this shape, now this is the maximum torque line or the line characteristics. This represents the angle, which I have angle setting, which is 85. This is one thing. Now, this represents the directional relay settings, like directional unit. So I know I can set the directional unit, which is perpendicular to the maximum torque line. So I know also the angle of this line. So I have the directional unit. So this is the directional unit. I know this angle, which is perpendicular to the 85 degree. Now, what is zone 1 and zone 2? Zone 1 here, the X. So I'll say X, so I'll take zone 1 impedance settings. I'll take the reactance, the X value of zone 1. So this is this axis. So that's zone 1, which is X1. This is another setting. The third setting is the zone 2 reach, which is this value. Okay, this is X2. Now, how do you find X1 and X2? X1 is the imaginary part of zone 1. Zone 1 setting before we apply. Zone 1 was 28 at angle 85. So 28 at cosine this give me the resistance. 28 sine this give me the reactance. So I'll take the reactance of that 28 sine 85. So that's X1 setting. And that's X2 setting. So this is zone 2 reactance setting. 42 for sine 85, get 41.8. So these two settings. So how many settings I have? The characteristic angle setting, the directional unit setting, which can be directly fine, and I have X1, the reactance settings of zone 1 and zone 2. And I need to know this line, I'll make it as, let's say, that color. So I need to know this line. So on this line, I have to choose this point at which it crosses the R axis. So I need to have this R setting. Okay, and similarly, you can choose for this line, and you need to check that value. Also, resistance settings. So, have the angle of this line is known, right? I can choose the same as the 85. So this angle also is 85 degree. Similarly, this is also, I can choose it in a relay. This is also 85 degree. But I need to know this resistance setting. So how do you choose this line? This line is angle. I have to know the resistance of the load. And I'll try to be away from that resistance by a safety margin. So let's find first ZL impedance. We know that ZL impedance. We know that this zone 2 and zone 1 has to be away from ZL so that there will be no problem of load encroachments. So what is ZL? What is ZL in this case? If I choose now, if I take 16.5 at angle 36, so ZL already, I didn't calculate here, I can find ZL. I'll write it in. So ZL is referred to the relay side is 16.5. Okay, that angle is 36.89. And now if I take real part of this in rectangular form, if you take the rectangular form of this, I don't have a scientific calculator, so it's this times cosine that. Let me check if I have. So if I have this 16.5 cosine 36.89, that's 13 ohm. 13 point almost 2 ohm plus J over I'll take sine which is 9.9. So this is the load. So this is R of the load, which correspond to this value, and X of the load, which correspond to that value. Okay. And now, so this value is 13.2. Okay. So this is the maximum load. So this is the minimum value of the resistance. At maximum load, as you can see from this, at maximum power flow, we have minimum impedance. And also when you take this minimum, we also measure it at minimum possible also voltage, even with so they get with the worst case scenario for the load impedance. Now with this impedance, 13.2, I want to be away from this by a margin. So get away from this. So I'll take at least 30% margin. Now take 30% margin. So I got 20 to 30% away margin. And in this case, I'll go for 10 ohm. My setting. 10 ohm away from 13. And so I choose this setting. So therefore, what are the three settings? Zone 1 reactance setting is 27.9. Zone 2 reactance setting is this. So this is, I can say this is also X1, X2. Okay. And what is X1 here? This is a horizontal line. So this angle is like, this angle is 0. Okay. And this is the resistance setting, the characteristic angle, okay, is equal to 85. So I have to specify all of this. This is the maximum torque line angle, and I have to specify directional unit angle, okay, which is this blue line, and this RC line angles will be 85 degree, and also this value. I have to specify even this one, okay, which I have not shown. So the zone 1 becomes this. So if any resistance, sorry, when the fault impedance falls inside here, okay, falls inside this area, this is means the side in zone 1, so it will instantaneously trip. When the fault becomes in this area, full area, Okay, means it is in zone 2, and in zone 2 it will be delayed by 0.3 to 0.4 seconds to trip. So in addition to this, I have also to set the time for zone 2, okay, because it's not automatic. Zone 1 normally is instantaneous, so it has you can set it at the lowest time, but zone 2 is it has to be set delayed by 0.3 coordination time. So that's three sort of examples that we have solved the problem of load encroachment when you use this polygon shape characteristics. Now the last part of this is the pilot distance protection. And pilot distance protection, or we call it also now how do you solve before I go here. Now if we have zone 1 and zone 2 at the sorry, we have two relay here to protect this line. So how do we and there is no communication between them, right? So on this is called, when you have no communication between a relay at the two ends, we call it a step distance relay, okay, or we call it standalone. Standalone, there's no communication between the two relays at the two ends. So RA protects the line in this direction, and so it has zone 1 red color here. This is zone 1 reach of relay RA, and zone 2 reach to 120% of line A. So this is zone 2 coverage, and this step above step is it represents the time, which is 0.3 seconds. So it's like I'm drawing this y-axis as time, x-axis is the reach. Okay. So I have this is the time settings of zone 2, and it's the reach of zone 2 up to here. And similarly, zone 1 of relay B that looks in this direction now this is zone 1, and zone 2 up to 120%, which is will cover up to here, and its time also, this is time 0.3 seconds, 0.3 to 0.4 seconds. Now there's no communication, right? So now when a fault in the overlap between the two zone 1s of the two relays, like a fault is here, then each relay will see this fault in zone 1, so it will give a command to their corresponding circuit breaker to trip immediately. So we achieve fast operation tripping when a fault in this gray area in the overlap between two zones. And when a relay falls in the end, either the last now, so assuming that we have zone 1 80% to 90%, so you left here either 10 to 20%, or now if we and here also 10 to 15%. If I use zone 1 as 80 to 90%. So for faults is here, this relay will see this fault in its zone 1, so it will instantaneously trip this breaker. But this relay will see this fault in its zone 2, so it will have a delay of 0.3 seconds to trip this fault. So we have a delay in this case, whether a fault is here or in this, so you'll have a delay of 0.3 seconds. And how do we solve this? By providing communication between the two relays, okay, to avoid delayed operation. Okay, so this is called channel aided, channel assisted, okay, channel, which is the communication channel, okay, or we call it also pilot. Pilot is referring to the pilot wire that connects the two relays, copper wire that connects this relay for communication. So the relays are sharing information now through the communication, which could be borderline carrier, you could use fiber optic, okay? Now the signals between them could be a permissive signal or inter-trip signal or blocking signal. I'll come to this. So how they will share the information between them over this communication channel. So that we want to achieve fast operation, okay, for any fault within the protected line. We don't want to wait 0.3 seconds, okay, time delay. So this can be, we have 4 schemes, okay, based on how these 2 relays are communicating with each other. The first scheme is called the directional or direct under-reach transfer trip, DUTT, and we say, and we have permissive under-reach transfer trip, permissive over-reach transfer trip, directional comparison blocking, and directional comparison unblocking. So 5 schemes here. When I say under-reaching, means we are using zone 1 as a criteria to send a signal to other relay. Okay, when I say overreach, means we are using something like zone 2 or as a criteria to share information. Okay. When I say direct transfer trips, means this relay sends a trip signal to the other relay also telling him you have to trip. This is direct transfer trip. When I say permissive, means the relay send a permission to other relay to trip. So the other relay can decide whether he has to trip or not, depend if he sees also a fault or not. Okay. When I say directional comparison and blocking here, its relay will send a blocking signal for the other relay to not observe this. I'll try to show you these schemes. So let's go to first one, direct and under-reach transfer trip. So we have 2 relays at the 2 ends. This is looking in this direction. This looks in this direction. And this is the logic. Now we have zone 1 that if this sees a fault, relay 1 sees a fault in zone 1, it will trip immediately, right? There's no time delay. If it sees a fault in zone 2, it will take a time t delay. If it sees in relay 1, zone 2 of relay A. And also we'll have time delay, okay, for zone 2. For zone 2. So if it is if it sees a fault in zone 2, it will wait this time and then it trips the breaker if the fault is not clear. So now what we'll do, because this is under reach transfer trip, if this sees a fault in zone 1, it will directly, if the zone 1 element picks up, it will send directly a signal through its transmitter through the communication channel and received by the receiver at the remote end relay to trip directly the relay. So this relay can trip whether it's instantaneously, whether it receives, detects as a fault in zone 1, or it received as a trip signal from the remote end relay. With this case, so even if the fault's very close to this one, which is zone 1 reach up to here 80%, and zone 1 and from this S rate up to 8%. So the fault is here. This relay at breaker 2 will not see this in zone 1. So it will, if I have no communication, this will take a time of 0.3 seconds to operate this. Because of this communication now, because this is on zone 1, it will send a trip signal to the other relay also to trip. So I achieve now instantaneous tripping for any fault within the line. This is called direct transfer trip. Fault here detected by zone 1, trip this breaker, transfer trip, and clear. So again, fault is here. This is send a trip signal direct, and this also clear, and the fault is clear in the sky. Now this is another scheme which is permissive overreach transfer trip. Now I will use permissive overreach. I'll use zone 2 transfer a permission signal. So here I have zone 1 reach up to 80%. This is zone 1 of relay A. This is zone 2 of relay A up to here. And similarly, zone 1 and zone 2 of relay B. And this direction, this is A and B. Now, this logic shows as follows. Now, if relay sees a fault in zone 1, it will trip instantaneously. If see it in zone 2, like here, okay, now a fault here, this is in zone 1, so it will trip this breaker. But this one sees this fault in its zone 2. Okay, so what it'll do, because it sees the fault in zone 2, and it will send now through its transmitter a signal, okay, to other relay, telling him I'm seeing a fault in zone 2. Okay, but this one relay also sees this fault also in zone 1 and zone 2. So its zone 2 also picks up. So this one also picks up. It will send also a signal to the other relay, telling him I have seen also a fault in zone 2. Okay, so it's already sees a fault in zone 2 and received a signal from the other relay telling him also I am seeing a fault in zone 2. So when both agreed that they see the fault in zone 2, they will trip. A trip signal is generated and trip circuit breaker P. Okay. And what is not shown here also, we didn't show zone 1 trip. So basically we have a signal from here, time delayed, and then it goes to zone 2, and zone 3 also. If I have zone 3, we have time delayed and goes here. This is zone 3 of A. This is time delay. This is a time delay 0.3 seconds. This is time delay of 0.6 seconds. Okay, time delay of zone 3. This is time delay of zone 2. Now we are just focusing on the communication logic. Okay. So this is widely used types of distance relay. We use it in also Bahrain here for protecting transmission lines. The third logics I want to show you here, the directional comparison blocking scheme. In this case, this scheme is used when you are talking about that when you use power line as a carrier, power line carrier for communication. Means using the power lines to communicate, to send a signal from one side to another. We don't have fiber optics. We use overhead lines itself as media to send trip information. Now, for fiber faults in the line, you cannot use it now the line to send a signal through it, a communication signal through the line, faulty line. However, when a fault outside, the line is healthy, whether it is here or there, the line is healthy, and we can utilize the transmission line as a communication media, a communication channel. okay, through which we share information, these relay. So in this scheme, it used a third zone. So it's not, let's say zone 4. A zone 4 which is directed backward. Okay, I will say reverse zone. ZR here is reverse zone for, let's say we have zone 1 which is protected instantaneously 80%, zone 2 to 20%, zone 3 it acts a backup, zone 4 now it looks backward. Okay, so this is the reach of uh, zone 4, okay, which looks backward, okay, it's not forward. Now now we make it, let's say 10% here up to, so if we talk about so we have to check if this relay sees a fault backward, like in this case, it will send a blocking signal for this, preventing it from tripping because this relay sees this fault in zone 2. Okay, and I want to block it. So this is the logic. So what does zone 1? Zone 1, sorry, relay A, it will it will first, if it sees a fault in zone 2. Now what happens? Relay 1 for a fault here, relay 1 will see this and backward, okay? And so means ZRA will picks up, it will be high. And at the same time, how do you know this relay, the fault is backward, not forward? It will check also zone 2 is zone 2. If it's zone 2 did not pick up, means this fault is backward because zone 2 is 100% forward. But the zone, reverse zone, is part of it forward, part of it backward. So it will see if also zone 2 of relay A did not pick up, so not here. So in this case, zone 2 for a fault here, zone 2 will not see this fault, so it will be a logic 0. So 0, it will be high now. With high, this will be signal high. This high signal will be transferred to the other end as high. And because this is high, logic 0 becomes 0. So it will prevent, so even this relay sees this fault in zone 2, it will take, let's say, 0.3 seconds delay to trip because of this 0 now, this is blocked by the other relay, so it wants to trip now, okay? Similarly, this is the called directional comparison blocking scheme. And this is the, there is other host schemes, so one of you can also present the project details about other schemes, which is directional comparison and blocking. So why we have all these advantages, disadvantages of each, okay? I will end up with showing you a relay, distance relay. This is a relay from GE. We call it line distance relay, transmission line distance relay. This is the manual of that relay. If we go and see what's inside this manual, just zoom. So it shows you the hardware, how to use this relay, how do you set it, specifications of this relay, wiring, how do you connect it, direct input-output communication for this relay with their fiber, okay, optics, or these are the channels, RS422 or RS, and you have so many things, control elements, the ground elements, which is the phase elements. So I'll show you now how the something related to the connection. So these are the inputs. The inputs, this to relay. I'll go to okay. This is the relay, which means you have different inputs. I have inputs which I can. This is RS232, so I can put my laptop and change the settings and read the metering values. I can throw this. I can upgrade a new software for this relay. I have output through which I can connect Ethernet port, through which we can send also signals to other relays, okay? Or I can access this remotely also to change settings. It can be connected to through a local modem or through RS485 for communication, okay, purposes. So if you go to the inputs, this is the so this is the functions inside. So this relay has to be, and they need a CT and a VT. Okay, this is the shows you the core balance CT, and it gives a trip signal to a breakers. Now here we have so many functions. This overcurrent functions. I will zoom it. The overcurrent protection for P, or for phase overcurrent relay, and for G normally for the ground overcurrent protection. So this goes measure the zero sequence current. It has the distance relay is the 21. 21 relay is this. 21 P means phase distance, and 21 G for the ground distance. This is 21 G. Okay. We have other functions like directional overcurrent. We have for synchronization. So other function other than the just distance relay. Okay, and it has metering. It can measure the power, and so this is one thing. Also show you how the characteristics for 21. This is for 21P. So on page 27, I think, the specification. Yeah, this is the ground distance or phase distance also. So the characteristics you can for this relay, you can use MO, you can use quadrilateral means characteristics. You can selectable individually per zone. So each zone you can make zone 1 as MO, or you can use it a quad. Similarly for zone 2, zone 3, zone. You have 5 zones here you can choose. You can have zone 1 forward, zone 2 forward, zone 3 forward, zone 4 backward. Okay, you have 5 up to 5 zones. Can be set as forward or reverse or non-directional. Means forward and backward. So like a circular. Reach, the pickup settings here for reach refer to the secondary side, means to the relay side, from 0.02 to 500 ohm and steps of 0.01. This is for the reach settings. And we have a list for the angle setting. we call it the characteristic angle. We have from 30 degree to 90 degree. In the example I show you, this is either 75 or 80. Here, from 30 to 90 degree in steps of 1 degree. Okay. A comparator limit angle, I'll show you this what we mean by comparator limit angle. Directional supervision for directional unit, you can set it from 30 to 90 degree and in steps of 1 degree. We have right blinder. I'll show what's the right blinders. We have left blinders, okay, and we have so this is like how fast it can operate. For a fault within 80%, this is zone 1. For 40 up to from 0% to 80% of the line. So it takes almost an average here for average of 20 milliseconds. So from 10 to 25 milliseconds depends on the source impedance ratio, the impedance of the source with respect to impedance of the line, protected line. So that's 20 milliseconds, which is about 1 cycle time. Similarly, for ground elements, we have also all same characteristics. I'll show you also the wiring diagram in page wiring diagram in page 36. This is the wiring diagram. How do I connect this relay to its inputs? So I have CTs, the 3 CTs for each phase connected to the either I can choose 5. And this relay accept either 5 ampere as input or 1 ampere, depends on this CT. If I choose 5 ampere CT, I will connect it to the 5 ampere input, okay, which is this one. And similarly, this is the ground. So a summation CT is just a CT here, which will be taken to the ground, IG5. For the voltage, I can have star VT, and the input goes to the VT, voltage A, phase B, phase C, okay, voltages. And for the trip, this is the output trip, okay, the trip contacts from here. This is the output H1A and H1C. So this is the trip coil of the circuit breaker. So this is contact closed, relay trips, and this is also contact of the circuit breaker is closed. So this will be trip coil of circuit breaker will energize and trip this circuit breakers. Now we have also like this is RS232, so that I can connect computers to this, so to change settings. It shows you have also to receive a trip signal or permissive signal from other relays. We have input digital through RS485 inputs. This relay can receive or can send, okay, a signal to other relay. So either through fiber optics, this is for fiber optics, or this is for RS485, okay, communication ports. We have also, I would like also to show you the 558. A lot of details in this manual. go. This is the architecture of this relay. You have CT and VT inputs to a DSP to A to D converters. It can also receive from analog also inputs as from RTD. Okay. Also, so this is the measurements units. We have the so we have here the logic, we have the measurements inside, control, processor, and we have the trip, output contact strip relays. I'll show also the, which is the most important things, is the 85 here. The 85. Where is the characteristics that this is what I want to show you mostly. 85, which is this one here. 85, yeah. This is the more characteristics for phase distance elements, okay? Or this is phase distance elements. Okay, as you can see from this characteristics, this is a more characteristic, but can be shifted. Depends on, this is the reach, this is the setting. This is the setting of that. Now I can shift this characteristic, this direction or this direction by choosing the RCA. Okay, RCA means relay characteristic angle. Okay, I can choose this 80, 85, 86 by steps of 1 degree. Now, once you find zone 1, we'll say we find zone at 85 degree, I will set this at 85 degree. This is the reach setting. Now, directional unit, we have another directional unit, which is, this is the directional unit setting. It has a directional relay characteristic angle, which is this is like the maximum torque line angle. I can set it in line with the reach or at a different angle. Now we can also choose the direction relay angle. You can set its also maximum compensation limits. So this you can also what is this? You can make. I'll show you later. By all of this control, you can control this characteristics. You can. This is offset mode. You can have a backward reach and a forward reach. So you have offset mode. Okay. This which becomes non-directional. If you set this offset mode, sorry, the backward, and same as forward, become as full circle centered here. This is the quadrilateral characteristics, where we have this directional unit. This is directional, another unit. This is a blinder. This is another blinder. We call it the blinders. So these are, this line is a blinder lines, and this is the reach of the settings. So this is my reach. So I have this angle setting. I have to know this line characteristics and this characteristic, the angle of this. Okay, this point, which is a left, the right point that we have set R, right, setting. So you can adjust this line with this horizontal, or you want to tilt it also. So you have a lot of, you can control over this. So with this more, you can have more like this one with this settings. You can make it like this, okay? You can make it like this, or you can make it as a lens. By just choosing those settings, controlling these settings, you can adjust the shape of the more even. You make it lens. And similarly, you can shape this polygon shape. I can make it like this, or I can make it clipped like this. Okay, you can make it any of these shapes. And with this, I would like to close this chapter. I'll stop recording.